The Earth is heating up fast compared with other times in our planet's history. This rapid pace has been going on for about the last 150 years, and especially in the last few decades, both over land and at the surface of the ocean. Why is this happening? What's the main cause, and what's the evidence for this cause? Keep watching to find out. In a previous video, we showed how models are really useful for separating out the different factors contributing to the Earth's temperature rise. But there's also another way of figuring out the main cause of this heating, and it involves direct evidence that's in the atmosphere. Before we get to that, let's talk about some things we know. We understand the science of the greenhouse effect, which explains how certain gases in the atmosphere cause warming. There are gases in the atmosphere like carbon dioxide, methane, and water vapor that absorb heat energy from the Earth and effectively trap some of it, keeping our planet nice and warm. We call these gases greenhouse gases. This is not unique to Earth. For example, Venus has a greenhouse effect in its atmosphere. We depend on the greenhouse effect. Without it, the planet would be too cold for us to live. But if a lot of additional greenhouse gases are added to the atmosphere and they persist there, it heats up the planet to a point that's problematic for us in a lot of different ways. And that temperature change also leads to other changes in things like rainfall, snowfall, drought, storms, and sea level. What do we know about one of those greenhouse gases, carbon dioxide? We know that carbon dioxide, also called CO2, has built up in the atmosphere over the last 150 years. Scientists can measure this. This graph shows the concentration of CO2 in the atmosphere in units of parts per million, or ppm, from 1880 to 2024. Where do these measurements come from? The data from 1958 to now come from air samples taken in Hawaii, and the older data come from ice cores from Antarctica. Ice cores are cylinders of ice that are extracted from the Antarctic ice sheet, the Greenland ice sheet, and mountain glaciers around the world. The cores contain annual layers, so you can date them, sort of similar to the way we date tree age with tree rings. And the deeper you drill, the farther back in time you go. In one of the photos shown here, the researcher is holding up a sign that says 2,000 meters. That's more than a mile, so the drilling went very deep into the Antarctic ice sheet. The ice contains tiny air bubbles that capture the air from when the ice formed, and those bubbles contain a record of the chemical composition of the air in the past. And that's one way we can learn about past levels of atmospheric CO2. The previous graph went back about 150 years, and that's the main time period we're focusing on in this video. But it's also important to have a much longer-term perspective of how CO2 has changed. And here you'll see an extension of the previous graph going back 800,000 years. That's how far back in time the Antarctic ice core data go. What you see is that hundreds of thousands of years ago, there was a cycle of natural variability with CO2 going up and down. Then, in about the last 100 years, CO2 concentration has shot up far out of the range of natural variability. And the rate of change now is much faster than in the past. We see sometimes a rapid increase of CO2, but let's look at the numbers. Around 250,000 years ago, CO2 increased by 80 parts per million in a little over 8,000 years. By comparison, today it's taken only 42 years for atmospheric CO2 to increase by that same amount. So clearly that's much faster than one of the fastest times in the past. It's like comparing the speed of a jet plane to the speed of a turtle. And we know that through the mechanism of the greenhouse effect, these changes in CO2 can change the Earth's temperature. The question we want to investigate today is, what is the main source of the CO2 that's building up in the atmosphere? Scientists discovered hundreds of years ago that burning things like wood, candles, oil, and coal releases carbon dioxide. And we know that people have been burning more and more coal, oil, and natural gas as our society has industrialized over the last 150 years. We have records of the amounts. These fuels are called fossil fuels because they formed from the fossilized remains of ancient plants that lived millions of years ago, either on land or in the ocean. When those plants died in environments where they didn't decompose, they fossilized and the carbon they contained was stored underground, and we can extract those sources and use them as fuel. This is an illustration from an 1861 issue of Vanity Fair magazine, and the caption says, "Grand ball given by the whales in honor of the discovery of the oil wells in Pennsylvania." The whales are happy that they won't be hunted anymore, and most people are probably happy that we've stopped hunting whales for whale oil to light our homes. Fossil fuels have made a lot of things possible for us, but combustion of fossil fuels does add carbon dioxide to the atmosphere. We've talked about fossil fuels, but other things could be adding CO2 to the atmosphere as well. Could the CO2 be coming mostly from volcanoes or outgassing from the ocean? The CO2 might come from fossil fuel combustion, but could it come from some other human activity, like deforestation or agriculture? And if that's the case, which one of these is the dominant source? It turns out that the atmosphere contains direct evidence of the main source of that CO2. You can think of it like a fingerprint in the atmosphere. Let's investigate. To start, we'll need to know a little bit about the chemistry of atoms. Atoms contain particles called protons and neutrons, and chemical elements such as carbon have different isotopes, forms of the atom that have the same number of protons, but different numbers of neutrons. For example, the 3 isotopes of carbon shown here, carbon 12, 13, and 14, all have 6 protons, but each one has a different number of neutrons, 6, 7, or 8. The more neutrons, the heavier the isotope, so carbon 13 is heavier than carbon 12. This simple fact will turn out to be an important part of our investigation. Carbon 12 and carbon 13 are stable. They don't change over time. Carbon 14, however, is not stable. It's radioactive, and over time it will decay, meaning that its atomic structure will change, and what once was carbon will become nitrogen. Let's first talk about carbon 12 and 13 in the Earth's climate system. The air around us contains both of these isotopes, and plants take in both of them through photosynthesis, which is the process by which plants generate the energy they need to live. But it turns out the plants preferentially take in carbon 12 during photosynthesis. Some of that carbon returns to the atmosphere, but some is stored in leaves, stems, and wood. Because of this, and since carbon 12 is lighter than carbon 13, plant carbon is lighter than carbon in the atmosphere. Fossil fuels come from ancient plants, so the carbon they contain is also lighter than carbon in the atmosphere. We can quantify the relative heaviness or lightness of carbon in materials, including CO2 in the atmosphere, by defining a quantity called delta 13C, and I'm showing you its definition here. You don't need to remember this equation, but the key thing to know is that it contains within it the ratio of carbon 13 to carbon 12, so you can think of it as a measure of isotopic heaviness. Now on to the evidence. What you're going to see is a graph of this quantity, delta 13C, for carbon dioxide in the atmosphere over time, from 1980 to 2020. So scientists have taken air samples over these 4 decades, analyzed the CO2 in those samples, and computed delta 13C. These particular air samples were collected at the Mauna Loa Atmospheric Observatory in Hawaii. When you see the data, you can keep in mind this scale on the left, which indicates that data points higher up on the graph have heavier carbon, and data lower on the graph have lighter carbon. Here come the data. we see a steady downward trend in delta 13C over the last 40 years or so, meaning that the carbon in the atmosphere is getting lighter over time. What conclusions can we draw from this evidence? This data set can tell us about the source of the CO2 that's building up in the Earth's atmosphere. Let's go through a list of suspects, keeping this graph in mind. All of the processes listed here release carbon dioxide to the atmosphere, so they're all suspects. Let's go through them one by one. When people cut down or burn forests, the carbon those forests stored is released into the atmosphere as carbon dioxide. Forests are often cleared to build farmland, so deforestation is related to our next suspect, agriculture. Now, agriculture uses fossil fuels, like the fuel to run this machine. For this investigation, we'll put that in the category of fossil fuel burning. But even putting that aside, some agricultural practices disturb the soil in a way that promotes the release of carbon dioxide. Volcanoes release carbon dioxide when they erupt. The ocean both releases CO2 and takes it in. Could it be that the ocean is releasing more CO2 than it takes in? And fossil fuels release carbon dioxide when we burn them. For example, when a car's engine burns gasoline, the octane in the gasoline reacts with oxygen from the air to form carbon dioxide and water. So which suspect is primarily responsible for the carbon dioxide that's been building up in the atmosphere? To answer this question, let's look at where these suspects fall on a scale of light to heavy carbon with respect to each other and relative to the atmosphere on that scale. The carbon that's released from volcanoes is a little heavier than what's in the atmosphere. The carbon from the ocean is about the same in heaviness as the atmosphere. And the carbon released from deforestation, soils disturbed by agriculture, and fossil fuel burning is much lighter than what's in the atmosphere. Now back to our evidence. The fact that the proportion of heavier carbon in the atmosphere is going down over time means that whatever is adding carbon to the atmosphere has to have lighter carbon than what is already in the atmosphere. So we can eliminate two suspects, volcanic eruptions and ocean outgassing, and the main culprit has to be deforestation, agriculture, or fossil fuel burning. The carbon they release is lighter than what's already in the atmosphere. Now, how do we separate out the contributions of these three suspects? We go back to our isotopes, this time looking at radioactive carbon-14. Remember that carbon-14 decays over time. The decay time is characterized by something called a half-life. Carbon-14's half-life is 5,730 years, which means that if you had a sample of some material containing carbon-14, only half of the original amount of carbon-14 would remain after 5,730 years. In another half-life, only a quarter would remain, and so on. One consequence of this has to do with plants and their fossilized remains. Plants living today contain all three carbon isotopes, but coal, which formed from plants that lived around 300 million years ago, will only contain carbon-12 and carbon-13. Any carbon-14 originally contained in the plants that turned into coal will have decayed a long time ago, because 300 million years is many, many carbon-14 half-lives. The same is true for other fossil fuels like oil and natural gas. They formed from ancient plants, so they don't contain carbon-14. To use this information, we'll turn to another piece of evidence. And here we have to be careful not to be fooled by something else going on. This is a graph of carbon-14 in atmospheric CO2 from 1950 to almost 2022. You initially see low levels of carbon-14 and then a spike in the late 50s and early 60s, followed by a decrease. That spike was caused by above-ground testing of nuclear bombs. After testing was banned, and as the ocean and life on land were absorbing that carbon-14, its level in the atmosphere has been decreasing. That decrease has been speeding up, faster than scientists would expect from absorption of bomb carbon. And as of 2021, levels were down to pre-bomb spike levels, and they're still decreasing. So now, after the effects of the bomb spike have worn off, it's clear that something else is contributing to the decrease. The carbon dioxide being added to the atmosphere must come from a source that has a low level of carbon-14. Contributions from deforestation and agriculture would have relatively high carbon-14 signatures. They come from recently living plants, so the carbon-14 they contain wouldn't have had time to decay away yet. Remember, the half-life of carbon-14 is over 5,000 years. Fossil fuels, on the other hand, contain no carbon-14. It's the only source that would lead to the trend shown in the graph. So fossil fuel burning has to be the main culprit. Deforestation and agriculture are adding carbon dioxide to the atmosphere, and it's important that we work on reducing emissions from these sources, but they are not the main contributors. The isotope data uniquely fingerprints fossil fuel carbon as the dominant source. This is why we hear so much about decarbonization, moving away from fossil fuels to generate electricity, heat our buildings, and power our vehicles, and switching instead to energy sources that release far fewer greenhouse gases. These are sources like solar, wind, geothermal, hydro, and nuclear. Another huge advantage of these sources is that many of them are renewable. We won't run out of sunshine, wind, and heat from within the earth. The fingerprints of fossil fuels in the carbon dioxide in the atmosphere tell us the main culprit when it comes to heating up our planet. Since we know what's going on, shouldn't we make a change?